You gaze upon the surface of the ocean, a smooth expanse, lightly disturbed by ripples. Nothing. Empty. No ships, no buoys, no traces on the water. Just an utterly ordinary stretch of sea, hundreds of miles from shore. Yet just beneath this surface, at a depth of 300 meters, an object moves silently. A steel cylinder, 170 meters long and 13 meters in diameter. Inside, it houses a nuclear reactor, 16 ballistic missiles with nuclear warheads, and a crew of 107. It glides through the depths at over 20 knots, surfacing for weeks, sometimes months at a time. No one above knows where it is. Not satellites, not planes, not surface ships. Its very purpose is to remain unseen. This is a nuclear submarine. But here's what most people don't understand. A submarine is not merely a ship that can dive. It's a fundamentally different engineering concept. A surface vessel contends with one environment, water beneath its hull and air above it. A submarine exists within an environment that exerts pressure from all sides simultaneously. And that pressure is no abstract concept. At a depth of 300 meters, every square centimeter of the hull experiences a force of 30 kilograms. Across the surface area of the submarine's hull, that totals hundreds of thousands of tons, uniformly compressing the steel shell from every angle. One micro crack in a weld, one area of weakened metal, one seal that has lost its integrity, and water under 30 atmospheres of pressure rushes in with a speed and force that no manual means can stop. There's no emergency surfacing in 5 seconds at these depths. There are the laws of physics, which give the crew mere minutes, sometimes seconds, to react. Every element of the submarine, its hull shape, steel thickness, reactor power, ballast tank volume, propeller design, is a balance between diving depth, speed, stealth, and survivability. Increase the depth, and a thicker hull is required, making the vessel heavier and slower. Increase speed, and noise levels rise, making the submarine detectable. Reinforce the hull, and you lose internal volume for equipment and crew. Each parameter is a compromise, and the cost of error is not just lost cargo. It's 107 lives and a nuclear reactor resting on the ocean floor. Today, we will explore how a submarine truly operates, not at the level of it fills ballast tanks and sinks, but at the level of the physics that makes underwater navigation possible and the physics that makes it deadly. Let's begin with a fundamental question. How does a steel cylinder weighing thousands of tons submerge and then return to the surface? The principle is the same as that of a surface ship, the Archimedes principle. An object in a fluid is buoyed up by a force equal to the weight of the displaced fluid. However, while a surface ship remains in a state of positive buoyancy, its weight being less than the weight of the displaced water, a submarine must be able to switch between 3 states. Positive buoyancy means the submarine is lighter than the displaced water, allowing it to float. Neutral buoyancy occurs when the weight of the submarine exactly equals the weight of the displaced water, enabling it to hover at a designated depth without ascending or descending. Negative buoyancy means the submarine is heavier, causing it to sink. Transitioning between these states is achieved through ballast tanks, large compartments situated between the sturdy and lightweight hulls. At the surface, these tanks are filled with air. The submarine is lighter than the water. It floats. To dive, the ballast valves, known as kingstones, at the bottom of the tanks are opened, allowing water to fill them while displacing air through valves at the top. The submarine becomes heavier. Its buoyancy shifts to negative. It descends. To surface, compressed air from high-pressure tanks is pumped into the ballast tanks. The air forces the water out through the kingstones. The submarine becomes lighter. Its buoyancy shifts to positive. It rises. It sounds simple, but in practice, This is a process of exquisite precision. At operational depths, a submarine must maintain a state of nearly perfect neutral buoyancy. Nearly, because absolute neutral buoyancy is unattainable. The density of seawater varies with depth, influenced by temperature, salinity, and pressure. A submarine perfectly balanced at a depth of 100 meters may feel slightly heavy at 200 meters due to changes in water density. The consumption of fuel, water, and provisions continuously alters the weight of the vessel. A torpedo launch instantly subtracts 1.5 to 2 tons. All of this must be compensated for. To finally adjust buoyancy, submarines utilize balancing and trim tanks, small compartments where water is either taken in or pumped out in quantities of tens or hundreds of liters. Transferring water between the bow and stern trim tanks allows for changes in trim, tilting the submarine forward or backward. This balance management is, quite literally, a continuous operation, happening every minute throughout the voyage. Another means of controlling depth involves horizontal rudders or hydroplanes. These movable surfaces, located at the bow and stern, function like an aircraft's elevators. As the submarine moves, water flows over the hydroplanes, and altering their angle generates a force that directs the bow upward or downward. However, hydroplanes only operate while the submarine is in motion. A stationary vessel cannot adjust its depth using them. Now, let's talk about the hull. This is where the physics that distinguishes a submarine from everything else that floats comes into play. Most modern submarines feature a double hull design. The pressure hull, the inner structure, serves as the load-bearing component, designed to withstand the water pressure at depth. The light hull, the outer structure, gives the submarine its streamlined hydrodynamic shape and houses ballast tanks, piping, antennas, and other equipment that doesn't require pressure protection. The pressure hull is a cylindrical shell made from high-strength steel, reinforced with circular frames. The cylinder is the optimal shape for resisting external pressure. A sphere would be even better, but it's impractical for accommodating equipment and crew. The cylinder strikes a balance between strength and functionality. The thickness of the steel in the pressure hull ranges from 30 to over 50 millimeters, depending on the calculated diving depth. This steel is specialized, high-strength material with a yield strength of 600 to 1,000 megapascals. For comparison, standard structural steel has a yield strength of 250 to 350 megapascals. Submarine-grade steel is 2 to 3 times stronger. Moreover, it must remain weldable, since the pressure hull is assembled through welding, and each weld must be at least as strong as the base metal. This presents an exceptionally complex metallurgical challenge. High-strength steels are inherently more difficult to weld. They are prone to forming cold cracks in the heat-affected zone, the area near the weld where the metal has been heated and cooled during the welding process. A crack just a few millimeters long, unnoticed during inspection, could become a failure point at depth when the water pressure escalates stress in that area to critical levels. But this raises a question. If the pressure hull can be made from even stronger steel, or even titanium, as was done with Soviet submarines of Project 705 Lira and 685 Plavnik, why not dive to 1,000 meters, to 2,000, to create a vessel impervious to any anti-submarine weapon? And this is where the wall of limitations begins. First and foremost is mass. A sturdier steel allows for a thinner hull at the same diving depth, or it can maintain thickness while diving deeper. However, every material has its limits. Titanium is lighter and stronger than steel. Soviet submarines made of titanium could dive beyond 1,000 meters. The record belongs to the K278 Komsomolets, a Project 685 submarine, which reached a depth of 1,027 meters in 1985. This is a depth that no other combat submarine in the world has achieved before or since. Yet, titanium is extraordinarily expensive and challenging to work with. The cost of a titanium submarine is several times higher than that of a steel one. Welding titanium requires an inert atmosphere, argon or vacuum, and absolute surface cleanliness. Just a microscopic trace of grease from a welder's finger can create a defect in the weld, invisible to the eye but fatal at depth. The Komsomolets itself perished in 1989, not due to hull failure, but because of a fire. An ignition in the aft compartment led to a loss of propulsion, surfacing and flooding. Out of 69 crew members, 42 lost their lives. A vessel with an unparalleled hull, capable of withstanding the pressure of a kilometer's depth, was destroyed by fire. Hull strength is not the only factor in survival, not by a long shot. The second limitation involves all the penetrations through the robust hull. A submarine is not a hermetically sealed capsule. Dozens of pipelines, cables, shafts, periscopes, antennas, and torpedo tubes pass through the sturdy hull. Each opening is a potential weak point. Every seal must withstand the same pressure as the hull itself. As depth increases, the requirements for seals grow exponentially. At a depth of 600 meters, the pressure on a torpedo tube seal with a diameter of 533 millimeters is hundreds of tons, striving to push water through any gap. The third limitation is noise. And here we arrive at the submarine's main secret. A submarine is primarily an acoustic machine. Its greatest weapon is not torpedoes or missiles. Its greatest weapon is silence. And its main enemy is not depth charges. Its primary adversary is the sound it produces itself. Water is an ideal conductor of sound. The speed of sound in water is about 1,500 meters per second, 4.5 times faster than in air. Moreover, sound attenuation in water is significantly lower. The sound of a working mechanism transmitted through the hull into the water can be detected by a sensitive hydrophone from tens or even hundreds of miles away. One unsecured panel vibrating at the frequency of the turbine's operation can compromise the submarine's stealth. One bearing with a microscopic defect creates a characteristic tonal line in the spectrum that an opponent's acoustic analyst can pick out from the ocean's background noise, much like a voice in a crowd. This is why nuclear submarines are the quietest machines ever created by humankind. Every mechanism inside the sturdy hull is mounted on vibration-isolating foundations. Turbines, generators, pumps, all are placed on rubber metal shock absorbers that absorb vibrations and prevent them from transferring to the hull. Pipelines are suspended on flexible mounts. Decks are covered with damping materials. The outer surface of the lightweight hull is coated with a special rubber covering, anti-sonar, which absorbs impulses from active sonar systems and reduces reflected signals while simultaneously being soundproof to keep internal noise contained. The propeller is the primary source of noise for a submarine. At high speeds, the pressure at the tips of the blades drops so low that the water boils, creating vapor bubbles that collapse with a characteristic snap. This phenomenon is called cavitation. The acoustic signature of a cavitating propeller can be heard from miles away. This is why the shape, size, number of blades, and maximum revolutions of a submarine's propeller are among the most closely guarded military secrets in the world. Modern boats increasingly utilize water jet propulsion systems instead of traditional open propellers, pump jets that encase the propeller in a ring channel, effectively suppressing cavitation. This innovation reduces noise but also diminishes efficiency and limits maximum speed. Once again, we face a compromise: silence versus speed. And this compromise has a name known to every submariner: quiet speed. This is the maximum speed at which a submarine remains undetected by the enemy's passive sonar systems at a given range. For contemporary nuclear submarines, this speed is estimated to be between 5 and 8 knots. At this pace, the the submarine is quieter than the ambient ocean noise, blending seamlessly into the natural sounds of the sea. The crashing waves, the patter of rain, the calls of marine life, and the distant hum of ships. Exceed the quiet speed, and the noise will escalate. The turbulent boundary layer on the hull will start generating broadband noise. The propeller will approach the threshold of cavitation. The vibrations of the machinery will intensify. The submarine will sound off, and somewhere, hundreds of miles away, an acoustic operator on an anti-submarine vessel or another submarine will turn their head to the screen and say, "Contact." Now, let's return to where we began. A steel cylinder at a depth of 300 meters. You perceive it differently. This is not merely a diving ship. It is a system where every parameter is caught between irreconcilable demands. The diving depth is neither maximum nor minimum. It is precisely the depth at which the hull withstands pressure with a safety margin. The submarine remains elusive to most anti-submarine measures, and the hull's mass still allows for sufficient buoyancy for the reactor, weapons, and crew. The speed is just right for the submarine to position itself within a reasonable time frame, but not exceeding the detection threshold. The reactor's power is calibrated to support this speed and all onboard systems while minimizing noise. This is not about diving to the maximum depth. It's about navigating a narrow operational corridor where depth, speed, noise, strength, and autonomy balance each other. A misstep in any direction disrupts this equilibrium. Deeper, the hull won't hold. Faster, it will be detected. Quieter, too slow. Stronger, too heavy. And within this corridor lie hidden advantages rarely discussed. The ocean itself aids the submarine in its concealment. The thermocline, a layer of water where temperature drops sharply with depth, acts as an acoustic mirror, reflecting sound waves and creating a shadow zone where surface ship sonar is blind. An experienced submarine commander uses the thermocline as a shield, hiding beneath it, knowing that the sound of their vessel won't penetrate upwards. Deep water sound channels allow the submarine to listen to the ocean for hundreds and thousands of miles, distinguishing the sounds of distant ships, submarines, and even earthquakes, while remaining unheard. The ocean is both a prison and an ally. And therein lies, I believe, the grim beauty of the submarine. It is not just a vessel or merely a weapon. It is a machine designed to exist on the edge between buoyancy and sinking, between silence and detection, between hull strength and ocean pressure, between the crew's life and the physics of depth. Every submarine mission is a negotiation with the ocean, which presses on every square inch of the hull and listens to every sound within. And each time the submarine returns from a mission, it signifies that the balance has held. This time. And here's what I've been pondering. We've talked about pressure and stealth, but we haven't discussed what happens inside that sturdy hull when 107 people live in a confined space for months. Where does the air for breathing come from at depths where there is no atmosphere? How does the submarine produce oxygen, remove carbon dioxide, and maintain a life-sustaining atmosphere inside a steel tube underwater? I've created a separate video that delves into these details. You'll find it on the channel.